question, right? That's step one. The whole question is to characterize the whole array. Okay, we're going to go for the second part today. So now I'm up to the topic of filtering, which is what happens when you combine observations from either multiple sensors or the same sensor over time. Or maybe the same sensor gives you different observations at different times, or maybe some combination of the two. You have multiple sensors giving multiple observations, that's fine. We'll not do too much of that complication, but so that's what I refer to as filtering. There's two kinds of topics here based on what I just said. There's spatial filtering, which I'll refer to, which means that we're getting observations from multiple sensors that are just placed around in the environment, let's say, and we need to combine that somehow. Versus temporal, which really starts to get more complicated, but more relevant to it in many ways. And that is when we incorporate information from a sensor at discrete stages. Like we get a new observation and we have to update our information. We get another observation, we have to update our information. The first one, everything just happens simultaneously. I got a bunch of observations at once, and I need to do something about it. And as I said, you can combine these together so you can make spatio-temporal sensors if you like. That's perfectly fine. So spatial filters, let's talk about that. Here's a picture from an old book. I got this off of Wikipedia, though I didn't actually find the book. Anybody figure out what they're trying to do there? It's from China. Quite a bit old, I guess, right? So, nearly 2,000 years old. And let's see, if you want to figure out how high the mountaintop is there, you stand here and look at this angle. You stand here and look at this angle. And maybe it tells you, right? Right, so an ancient form of triangulation. So let's take a look at stuff like that. Here's the idea. I take any n sensor mapping. So I have n sensors here. So that's why I call h sub I. They go from h1 to hn. And I'm going to define a notion of triangulation. And I'm going to do it in terms of preimages. So in terms of the slices of bread from those sensors. I do the following. I say the triangulation of a set of observations is just the intersection of their preimages. Does that make sense? It should be that because that's all you can do to make the state consistent with all of the observations. The true state has to lie in this intersection. And the true state cannot be outside of the intersection because otherwise one of the sensors would have given a different value for observation. So that's all I'm talking about. In other words, you just look at the intersection. This common intersection here is the triangulation that I write with a triangle. Now I should be careful. What does triangulation mean for most of you, right? Take a polygon and break it into triangles, right? So it has nothing to do with that, as far as I know. In fact, I think this term is older than the triangulation used in computational geometry, if I'm not mistaken. This is ancient triangulation, really, to triangulate based on observations. People have used it for a very long time, for star charts and all sorts of things. Okay, let's see. So just an intersection of preimages, it's a different kind of triangulation than one might often talk about in computational geometry. Here are some examples. And these are fundamental things that people spend a lot of time on, but in terms of preimages, we can understand them in a very simple way. Here's one called stereovision, or stereopsis, if you like. So instead of making a two-dimensional image and a three-dimensional world, I deleted a dimension. So we have a one-dimensional image here and a two-dimensional world, and if we make a pinhole camera model, and there's an object that I'm observing, and say the object's a point, then I have in my one-dimensional image, it means the object appears in some place, right? So what does the preimage look like for that? It's a ray, right? I don't know if the ray, I guess I drew the ray from the image plane all the way out. Probably I should start at the pinhole, or I should really start at wherever the front of the camera is, right? But, you know, whatever. So I just drew it like this. And, but it is a ray, it doesn't matter where you start it. I think it goes off to infinity, unless you limit the depth of the camera, which I did not do here. And now, suppose I have two nicely calibrated in terms of location cameras. And isn't the principle of stereo just triangulation in this sense, right? So look at the green rays there, and remember this definition, intersection of pre-images is the triangulation. So think of stereo vision as just being the intersection of those two pre-images, right? That's how I can figure out with my eyes where Professor Mojades is, right? If I only had one eye, I would have a hard time knowing how far away he is. But with two of them, I can zoom in and I know exactly where he's sitting, right? So, well, okay, I can guess anyway because we've all learned a lot about three-dimensional information, right? But if I were an idealized sensor like this, that's how it would have to go, right? Especially if the thing I'm observing is a point, let's say, so I have no idea of nearer or further based on the size. So it's just simple triangulation. I write it as delta y1, y2. Is that okay? And again, I can make noisy versions of this. I can add disturbances and all kinds of complications, put probabilities everywhere. However, this principle of stereo vision is based just on this, which only uses the concepts from the previous part that did not have uncertainty in terms of disturbance and noise and probabilities. This concept works in the idealized case, right? And then you just add probabilities on top of it if you have stochastic noise model. Let me give you another one. This is my Chinese picture that I had. This idea has been around, it looks like it goes back to ancient Greeks, Egyptians, and Chinese. My guess is the ancient Persians did it too, right? Everyone knows these, probably. Did people say that? Is there any ancient Persian texts that show triangulation like this? Like the equivalent of this kind of picture? If you can find one, show me. Those are always interesting. I think everyone brings out their... I think multiple cultures figured this out, right? So it's very nice. So here's the idea. If I see two landmarks, let's say I'm looking at those speakers in the back. There's one there and one there. And let's say all I know is the angle between them. So I have some nice device here and I can measure the angle between them from where I'm standing. What does the pre-image look like if I can do that? It turns out it's a circular arc. So if I go along a circular arc, you're probably a good computational geometer should know that, I guess. I don't know. But if I get too close to those speakers, right, I start going up like this, I'm getting closer and closer, the angle's getting larger, right? So if I get too far away, the angle gets smaller. But if I move along a circular arc, then it will work out perfectly so that this angle is preserved. I drew the pre-image as a double circular arc thing. Anybody know why? So maybe I don't know which one is to the left or which one is to the right. So if I take 2 points on the plane and I'm not even sure which one's to the left or right, then I get a double arc. If I know which one's to the left or right, I get a single arc. Right? So what does triangulation look like? Well, it's just intersection of circular arcs. That's what the ancient principle is that people have used, the ancient Chinese one, the picture that I showed, and so forth. If I now have a third landmark, like that speaker over there, I can look at the angle between any two pairs of them, and that gives me two arcs that are pre-images, and I just intersect those, and there you go. Very fast, I have trivialized, if you like, the ancient principles of triangulation. I mean, just really, you can write it with a bunch of equations, you can write it with trigonometry if you want. You can make it look really complicated, but I think it's important to just think that it's just intersection of pre-images. That's all you have. So same idea, just like stereo vision. This is triangulation that produces, this is intersection or triangulation that solves this ancient problem. Questions about that?
What is the notation of this Y1 and Y2?
Y1 and Y2 are the observations. They're really tiny up here. It's the angles between two pairs. So there's the upper one here and the lower one there, right? And so those are the two observations. And then when you intersect them using delta, that's just this thing again, right? That's just intersection here. I intersect the pre-images. And I drew the pre-images in green. So one of these, I guess this one, I think this one here is the pre-image due to Y2, and then the upper one is the pre-image due to Y1. And so by intersection, I figure out exactly where the pink point is located, the sensor. Other questions? So I think it's very nice. Think about spatial filtering as, you've seen these ideas before somewhere, right? So think of that as intersection of pre-images. Think of it as intersection of pre-images, nothing more. I find that very powerful because we can remove all of the algebra, trigonometry, every one of these problems has something complicated to do in terms of algebra. No offense to people who like algebra, but it's all fine. But it's really just simple intersection of pre-images. Yes?
In your definition, what does fix? But when you change your position, that when you change your space domain.
Yeah. So for this problem, the state space should be R2, I think. I don't know if it doesn't say that. So X is R2. I'm just trying to figure out where the pink point is, right? And then based on the pink point, and then I have these points here are fixed. The landmarks are fixed in the environment. I guess I could say subset of R2 because I cannot stand on top of the points, if you want.
So in the last one, the Chinese.
Oh, sorry.
Last one. Yeah.
Okay, the pre-image, yeah, the stereo. Yeah.
You've got two domain, two space domain. When you change the position.
Yeah. Well, it's the same state space here. I can move this point around, and then I'm looking, assuming I stay inside of the field of view of the camera, both cameras, right? So I have to stay inside so that both cameras can see me. Then, when I move around, the state is changing, let's say, right? If I move the sensor, I see what's going on here. Oh, this is very interesting. So there's like a duality here. Okay, so let's see. Here, the sensor is moving, and we're trying to figure out where it's at. So it's like a robot carrying the sensor. Here, the sensor is fixed. It's really interesting. I never noticed this for this example. Here, the cameras are fixed, so the sensors are fixed and their location is calibrated. You know where they're at. And then the thing you want to triangulate and figure out is moving, but it's not a sensor. Right? Is that okay? But they're both the same state space. It's just a different object that moves. In one case, the sensor moves, and in the other case, the body moves here. Yeah. Is that okay? Yeah. All right. Anyone else? No, that's interesting. I didn't notice. Here's another nice one. It's called trilateration. Trilateration? I don't know how you say that. Trilateration, I think. So that's the name of this method. This is how they, for example, figure out where you are when you use your cell phone. Right? I think they can do that here, right? I think they do that everywhere with cell towers and such. In the U.S., in fact, they can track anyone, and it's hardly anyone's aware that it's illegal, but they do it anyway somehow. It's like a very serious privacy thing. Not too many people know that they can be found. The whole history of where they've been has been recorded, and the cell phone companies sell it to companies so that they can market. They know information about you, basically. So it's horrible. Anyway, all right, let's see. So here's the idea. The sensor now is like your cell phone, right? And then there's a tower, and this can work in two different ways, right? I mean, maybe the sensor's at the tower, maybe the sensor's on the cell phone. So here I'm saying, imagine we are trying to figure out where we are, okay? And we have some kind of device. This one probably looks more like, let's say you have a laptop with a Wi-Fi card in it, and you're looking at different signal intensities. So suppose I know how far away the tower is. Maybe I don't know. I only know, it could be that I only have the intensity, and I just know that as I get further away, the intensity goes down, right? It could be like that. But let's say here, I know how far away the tower is. If that's the case, then the pre-image is a circle, right? Well, if sometimes this is based on time of arrival, by the way. If you know how fast the signal propagates, maybe the tower transmits a signal, a sound, or a radio signal, based on the time of arrival, TOA, maybe some other kind of pulse or something, you can figure out how far away it is. So that's what it's called TOA, time of arrival. The pre-images are circles, or in R3, if we made a three-dimensional version, they would be spheres, right? And then triangulation is just that. If I use only two circles, what happens? If I have two sensors, I just get 2 points, right? Generically, in general position. And then if I get three, I now know exactly what point I'm at after intersecting 3 of them. What people might do in practice is they might use 8 or 9 towers, maybe or 6 towers, let's say some more towers, because there could be noise in the measurements, right? But the idea, the principle of trilateration, if you want the theory of it, is based on this, right? That this should be sufficient to do that. Here's another one. This was used in World War II. to localize submarines. And it's based on something called time difference of arrival instead of time of arrival. I don't know why it's not on the slide, but instead of TOA, it's based on time difference of arrival, TDOA. You can look that up if you want. TDOA is another thing you can get. So, for example, if I have 2 towers, and all I know, maybe the 2 towers are synchronized with their message, and the message gets transmitted to me, and then all I know is the time shift of the messages. So that's time difference of arrival. I don't know how far away anything is. It turns out if I get an observation like that, like I observe that this message is 1 nanosecond later than that message, if I get something like that, then what I get, it turns out, is a hyperbolic surface for the pre-image. And so there's a method called hyperbolic positioning that's exactly based on this, which I think is very, very interesting. And people built this thing, it's called the DECA radio-based localization system, or no, sonar-based, I think, for submarines in World War II. And it was based on this idea, so they had to take intersections of hyperbolas to hyperbolic sheets to figure out where the submarines are. So that's very nice. So there's 4 examples I gave that are quite common, let's say. Stereo vision, ancient forms of triangulation, trilateration, and hyperbolic positioning. So I encourage you to go find some more, right? You can come up with all kinds of methods for deducing where you are based on intersecting pre-images for whatever kinds of sensors you want to make. I also find it helpful to think about linear algebra here. So if I have linear algebra, if I'm going with linear algebra, I have linear sensors, let's say, and I have everything Rm and Rn, and I get a bunch of linear sensors. What's going to happen? Well, in that case, this is the way pre-images look. They're n minus k dimensional hyperplanes through the origin of x. Does that make sense? Isn't that what happens in linear algebra? What are those called? Kernels, I think, right? In linear algebra. So that's what you get. It's a set of all points that map to, you should get kernels are a set of all points that map to 0. Here you're going to get a set of all points that that can map to arbitrary. Oh, no, I set it up that way. That's right. So it has to be like that because these are y equals c of x. So that should be that way. All right, and then I get the by the triangulation. All you can think of that as is intersection of hyperplanes, right? So I keep intersecting and intersecting. Maybe I get a line or a point eventually. So I think that in some sense, the things that I showed you are, the methods that I just showed you are like nonlinear versions of this, right? So instead of being the linear case where I just intersect lines, I intersected hyperbolic sheets, circles, more circles, or rays in this case. So in linear algebra, it would look like the intersection of lines, and then you can do sort of basic, if you have linear independence, you can do dimensionality analysis here, right? Looking at rank to figure out how big the pre-images should be, and how big the triangulation should be, which I think is very nice. Right? So the nonlinear case has some more geometry. Like for example, for this case, we needed more circles because we can get multiple points because they're curved, right? 2 circles can intersect in 2 places. 2 lines can intersect in at most 1 place, right? So that's the reason why there's a little more happening here due to the geometry. But just by thinking about dimensions alone, you can get an idea of how the triangulation works. All right. Let me say a little bit about handling disturbances. So we could have non-deterministic disturbances. In that case, I imagine the pre-images are getting thicker. Right? So they get a little bit fatter here. And we end up with this. And in the case of probabilistic disturbances, we can write an expression like this, where we use Bayes' rule. And we have, these are probabilistic sensor models as I defined a little bit ago, in the last part of this session. And some kind of normalizing prior, let's say, so that I can say, what's the probability distribution of possible states? So instead of having these sort of rigid rings, you can imagine there's some kind of humps or something, and they look like nice probability distributions, still ring-shaped perhaps for this. And then what people typically do, if you want to take into account all of your observations, is they will try to find the state by doing least squares optimization, which is maybe justified if you have Gaussian models, right? It often happens like that. Usually an implication that you have Gaussian models when you do least squares minimization. In other words, I try to guess at what x is, that's x hat here, and I do it in such a way that the distances are all minimized right here, so that you don't even have to write in the probabilities if you don't want. You can do it so that the observations you get are explained in the best way, let's say, with respect to the state that you're getting, disturbed minimization. And that's what actually happens in a lot of real life, let's say, triangulation methods and such, is that you're overcoming disturbances, so you try to guess and minimize the error overall. In other words, what would be the least amount of total disturbance, right, that guessing the state that produces the least amount of total disturbance among all your observations. All right. So we can also go over state time space, and the same idea applies. So I can, for example, I go back to my funny z-space here, and I make these sensors, and then I can just say, well, we have triangulation over that, right? So now it's really odd. Now I've changed. It doesn't feel so spatial anymore. I have a bunch of observations, and each one has a pre-image that corresponds to some chunk of the state time space, and then I put them all together. And that's what that gives me. Interestingly enough, global positioning systems are doing that. There's a problem in global positioning systems in that, I don't know if you know this or not, but time synchronization is very, very important. How does that work? Let's see. If you're off by 1 nanosecond on the time, how far does light travel in 1 nanosecond? I think about 30 centimeters. So I think it's 30 centimeters. So you're already inducing some error. And 1 nanosecond, I mean, who has a watch that works down to the level of 1 nanosecond? Right? Imagine that. I mean, oh darn it, I have to reset it again. I don't know. It seems very difficult to maintain it. So what they're doing is they're simultaneously estimating the time and position all together at once. How do they do that? They do that by intersecting even more pre-images. And usually people know that the minimum number of satellites that you need for GPS to work is 4. I used to believe that it was 4 because I thought, well, here I need 3, right? And when I intersect spheres, I'm going to need 4, right? But I'm told that all of the GPS units assume that you're on the Earth, and so that's 1 more sphere. So it seems like you would only need 3 again, but the 4th one, the 4th satellite or 4th observation is being used for time, for time estimation simultaneously with everything else. So that whole method corresponds to intersection of pre-images over state time space. Now in practice, you know that it's helpful to have more satellites, and there's filters built on top that try to reduce the error, and they're doing this least squares type minimization, or maybe some other proprietary fancy thing, I don't know, but it's very interesting to think about it, that this state time space ends up being very, very important for global positioning, because the clock has to be perfect for that. Okay. Question? Right, I'm now going to move to temporal filters, so if there's no questions, I'll move on to the next part. Temporal meaning over time. Well, here's some questions I can ask. So let's say we have a state space and 1 sensor now. So I'm going to go back to the case of 1 sensor for a while. The previous topic of spatial filtering was with multiple sensors. Now I have 1 sensor, and I say, okay, let X tilde be the state trajectory. So state trajectory produces a state for every time. And it should be a continuous function for most of the things we do. However, remember these state spaces are very large. Sometimes it might not be a continuous function because of weird properties of the state space. But usually they are continuous in some appropriate sense. Y tilde is an observation history. That usually is not a continuous function because observations can jump all over the place. They can be weird discrete spaces that we have for the observation space. But that's the observation history. So what I want to imagine now is that since the beginning of time, going back to time 0, an observation is produced at every time. Right? So it's like a continuum of observations that I get now. That's the way Y tilde is. Imagine that. It's kind of ridiculous, right? No sensor will give you a continuum of observations, but this is just a limiting case. And we'll cover the discrete case in a bit when you have the discrete number of observations. But the continuous one is, I think, very helpful to think about. So here's something here. Number 1, here's a question I can ask. So based on getting Y tilde, right? So I have now my entire collection. It's like a spreadsheet, if you want, of all of the observations that I got. And I know exactly when I got them. So if I have all of that, here are 2 fundamental questions. So one of them is, what is the set of state trajectories that might have produced that? Okay. Which state trajectories are consistent with that? It's like another kind of pre-image, right? But this is over a bigger space. We'll have to think about that. And here's another question that's very common. where am I now? These are, what is the current possible state? X tilde of t, if t is some current time, let's say, or some particular time you care about, what could the state be right at time t? That's another question you can ask. So these are two questions. I just want to make sure you keep them separate. If I have the answer in number 1, do I have the answer in number 2? What do you think? All right. Almost, right? So if I have the set of all state trajectories, then I can look at that and try to, in fact, let's say it goes to the exact same t here. If I have the set of all of these, all I have to do is look at the possible final values for each one of these, not like this. All right? So 1 contains more information than 2. You can derive question 2. However, very often in robotics, we're interested in the answer to question 2 because we just want to know where the robot is right now so that we can make some appropriate action. How's it going? Sleepy? You guys okay? All right. Time parameterized sensor mapping. Let's think about this. So as I said, imagine applying h at every time. Right? So I have every time t prime between 0 and t, and I apply h. And then I get some observation. Now I make some really big spaces. I've already made capital X tilde. This one right there, I make capital X tilde. And so I have the set of all state trajectories there, right? All kind of time parameterized paths through the state space. So I could have a bunch of bodies moving around, or robots, whatever you like, all time parameterized paths. And now I have this capital Y, which is all possible observation histories. Remember the observation histories? It's kind of showing what happens up there with each t prime. But remember, it's the observation history. It's the entire sort of time parameterized collection of all observations. I'll have a simple example in a little bit. I just want to point out that once I give you h, there's this induced map. So it automatically follows from h over the interval 0 to t that we get a mapping from x tilde to y tilde. Does that make sense? Right? If I have a sensor definition and it works instantaneously at every time, and then I just keep applying it for all times, I can construct y tilde from x tilde. If I give you the whole state trajectory, that's enough to figure out the whole observation history. Is that okay?
Excuse me.
Yes.
Should X means our set of our sensors and depending our observations. You mean or not?
Yeah, there's 4 spaces here, so let's see. Make sure we get these right. So there's X, right, which is state space. There's Y, which is observation space. There's X tilde, which is the state trajectory space. And that's all functions that are parameterized by time and map into this space. Okay? And then there's Y tilde, which is the observation history space. And that's all functions that are parameterized by time and map into this space. So they look kind of very similar. So anytime you see a squiggle on top, I imagine it looks like a function. That's why I wrote it. Like as if there's a function on top of it. Okay. Thank you. Anybody else? So it looks as simple as that. If I write something like that, guess what I'm going to do? You probably know me well enough now that you would guess that I will make a preimage for that, right? Because that should tell you a lot. That should say, what are the x tildes, the little x tildes, the trajectories that are possible given the little y tilde, the history. That's how it should look. So that's how to answer the first question. Well, it doesn't really answer it, but it answers it with notation. And it just says, maybe it's hard to answer it in practice. So it says, given the observation, y tilde, what are the set of all trajectories such that using this induced map, capital H, I could obtain that observation history. How to answer the second question is the way that I already said. You just have to look at every stage in X, and if there exists some trajectory in that preimage, so that at time t is equal to X, then you should put it in the collection. So that's one simple way to write the answers to the questions. But that doesn't really solve any particular problem, right? It's just a notation of what to do. Is that okay? Let me give a simple example. I think this one's really kind of fun. So let's suppose the state space are those 4 line segments up there. And those are embedded in the plane. So those are subsets of R2. And then there's a point X that goes moving around. So that the point X up there, little x, corresponds exactly to the state. All right? So it's just a position of a point. As a one-dimensional state space, however, it has some interesting structure, right? It's moving on a planar graph along continuous edges, much like the way the evader moves in the old pursuit evasion on a graph problems, like that Parsons did in the 70s, if you know this. You like those kind of problems. So anyway, move around like that. So we have h of y. Now that's the observation. Now, if I get this observation, so all we get to see, you might imagine that we can't see the top part, if we're imagining how it looks to our senses. All we get to see is something like a movie. It's like a boring one-dimensional movie of a dot that moves back and forth along the line, right? If I see this in one instant right here, I know exactly where the x is, right? But if it's over here, in one instant of time, I can only narrow it down to 3 places, right? So it's very interesting. So that's the way H inverse looks. This is the standard for image of a single observation. It could be 3 points or 1 point. Or 2 points, if we're all the way over on the edge here. So this corresponds to 8 different ways the situation might look generically, right? If you think like in terms of critical cases, if the point is on the left, it could be in any one of these 3 levels, or it could be only on the top. Maybe I can only narrow it down to the top 2. Maybe the middle one I know, maybe the top or bottom, maybe the bottom 2, or I'm over on the right side, in which case I know exactly where I'm at. So those are the only 8 possibilities there. And let me make sure I get, and then, let's see, what do I have? So the particular edge, on the left here, I don't know what edge I'm in. And then, let's suppose, due to y tilde, the precise timing is known. So I watched the animation of this, and nobody sped it up or slowed it down. I get the exact timing of it. The reason why I care about the timing is because I'm reasoning about the set of possible trajectories, right? So I think if you watch this move back and forth for a while, you can reconstruct what it did, but only up to a finite collection of possibilities, right? If I took away the time parameterization, if somebody distorted the timing on the movie, then you'd have to describe a much larger family of trajectories because you don't know the exact time parameterization. It's very interesting the stuff that happens here, right? Like I can say initially, I have no idea where the point is, so then you're in this kind of case. And then if I see it move to the right, then you're in this case. What if it moves back? What case are you in? Yeah, that's very good. B and C case, which is this one. Right? Yeah, it's very interesting. There's interesting reachability here. This is the kind of information space similar to the ones that show up in pursuit evasion. But here it's just a very simple point with a very simple projection. You can do much fancier projections. You can put more complicated graphs in here, add more dimensions, and ask all kinds of interesting questions, even algorithmic questions if you like, about what these transitions look like, right? There's a big transition diagram inside of here for more complicated examples, and I think it's interesting to reason about those. No one's done that as far as I know. All right. So that's the idea. There should be a finite number of trajectories that are consistent when the movie plays. Right? And probably if you sat down, you could reconstruct those, right? It's not correct. Questions about that? Alrighty, so let's talk now about when I get observations at discrete stages. So this is much more common in practice. So rather than having a continuum of observations, which is what happens up at the top there, I instead get a sequence, y1 to yk. So my y tilde now is just a sequence of observations indexed by some I. Here's one of the first problems that we have. Between stage I and stage I plus 1, the sensor makes no observation. So what happens? Right? For example, maybe this point moves around. If there's a time interval where I cannot observe anything, who knows what happens, right? It can go quite far if I have unbounded speed assumptions like we have in pursuit evasion. So could get quite complicated. So that's one of the first things we have to pay attention to. If we want to get to the more, I don't know, realistic case of discretely indexed histories, where we have a sequence of observations, we're now going to have to deal with the problem of what happens between stage I and stage I plus 1, right? What happens during the interval of time when you get no information? All right, so a couple of things to know. That's what I said in number 2 here. Right? We need to model, in some sense, how the state might change over time when there's no observations. So we didn't care about that just a moment ago. Somehow you didn't seem to need that for this, right? For this problem, it didn't matter, because I have a continuum of observation. But if you don't have a continuum, you now have to declare what happens when you're not watching. Right? Will this point behave? What will it do, right? When nobody's watching. All right. But number 1 here, the other thing to pay attention to is that observations are going to arrive incrementally. Therefore, we're going to have incremental updating of information. So the filters now are going to look, what's the right word? Inductive. If you want a recursive backward, whatever. It's going to look recursive or inductive. It will be that here's the information state you have now, and oh, I have a new piece of information. I better update and incorporate that. So that's how that will look. So there are 2 characteristics that will become important now that we're doing temporal filtering. So here's the structure of how these look. Let I be any set. I'm going to start this off kind of very generically and then show some examples and such. But I find it kind of helpful just to say, okay, what is an information space? It'll be whatever it becomes in just a bit here. But just saying, for terminology, I will just start with some set I and call it an information space. And I will have some I0. I guess that's iota 0. It's a Greek letter, but is the initial I state. I'm using I state as a shorthand for information state. So whatever the initial information state is. I have something called a transition function, or we might call a filter, or temporal filter, which will look like this. It's a function phi. It takes the previous information state and the new observation, and it produces a new information state. That's how filters are going to behave. They're going to be keeping track of something, and I have to specify the transition function. When I do that, I've made a filter. I've made a temporal filter. The triangulation ones are another kind of filter, the spatial filter. The temporal ones are going to have this kind of structure. Sometimes I write it like this, where all I did was add +1 to all of the indices. It doesn't matter. Okay? So same thing, I just add +1 to all of these. The important thing to pay attention to is that these have 2 different indexes. This is up to now, and this is the new thing. So that's how it operates. First I get an initial information state, then I get a new observation, then I compute the new information state using phi, then I get a new observation, then I compute the new information state, and so forth. It goes on like that, right? That's the operation of a filter. That's how they run on robots like that all the time. They're getting information and updating and so forth. So that's the kind of generic way to look at the operation of a filter. And it's always the same function phi that's getting applied, which is this transition function. All right. Here's some very generic examples I will give, and then I'll start getting more specific ones. These are like the boring generic ones, I'll show, but they're quite helpful. So I could have direct sensor feedback. That's the information space is just Y. I could have something called a stage counter. It just tells me how many stages have gone by so far. I could have something that just corresponds to reporting the entire history. Or I could make something called a state estimator, which tries to get out the state from the information that it has. So those are going to be special cases that I'll look at. So, for example, if I just have sensor feedback, I don't care about the initial information state, and my filter is kind of trivial in the sense that it just ignores anything from the past, and it just outputs the current observation. Is that all right? If you can get away with this in a robotic system, if you can just hook a sensor directly to the robot and then give the commands to the robot based directly on the sensor value, you should do it if it works. You know, if it works for you, that's great. That means your filter is so trivial, and yet it still works really well. It's wonderful. That's perfect sensor feedback. Sometimes people call that reactive planning, if somebody's seen that around and such in artificial intelligence literature. Just the actions you take depend only on the information you have right now. It's a memoryless, right? All right, so that's one possibility. So yeah, reactive planning, you see that. stage counting filter. So maybe I have an information space that's just natural numbers. You can glue on the 0 there if you want. And I start off at stage 0. And then, well, guess what? What does the filter have to do? It just adds 1 every time, right? So, kind of worthless, I guess, but maybe that's all you need for some problem. Yeah, that's right. You were talking about the, Frank was talking yesterday about the squeeze grasping, right? So all you need to know for that is that you're done squeezing and it's time to go to the next step, right? So your strategy for that should just know how many steps there are. So this is just counting the steps. So that was sensorless manipulation. So, but so even the dummy sensor in some sense could be applied here, and then all you need to keep track of are the states. I'm trying to give these information spaces. Another reason why I'm giving them is that we're going to develop eventually an idea of planning where, I'm trying to motivate this just a bit here, let me take a break from that. I'm going to make a plan that looks like this. Here's a plan called pi. It's a function from an information space into U, where U is the action space. Or it looks like an input space in control theory, if you want. So in other words, I'm trying to figure out what kind of filter to make, what type of information space to make, so that I can make a plan to execute on a robot, for example, that says what action to take based on the information state. So in the case of like the case that the front talked about yesterday, it would be that all I need to know is what point are we at in the plan, and then we can continue on next. Whereas the previous one here would say, all I need to know is what the observation is right now, and then I can do it. So that would look like a special case. That one looks like a special case where it's just pi goes from y to u. Is that all right? That's coming in the future. I'm going to explain that in a couple of days, but I just want to give you a hint of why there's these weird information space things coming up. That's going to be precisely the information that a robot uses to specify what action to take next. Okay, stage counter filter we said. This one's kind of like the analogous to the bijective sensor. The bijective sensor was the all-powerful sensor. This is like the all-powerful filter. What does it look like it's doing? It just concatenates on the current observation and just maintains a big sequence for you. So all it does is just say, oh yeah, I'll write that down for you. Okay, I'll write that one down for you. And that's all it's doing. It's just writing down the observations. So the previous two I showed you were throwing away a bunch of information, which maybe is a good idea for some problem. This one is kind of a boring way, it just writes everything down. So it's just doing concatenation of the history, if you like. We should consider that, but I hope that when we make a plan later, we don't need an information space that's that big. That's going to be the goal, not to make the biggest, most ridiculous information space possible, because guess what? You have to specify a plan over the domain, which is going to be all sequences that you get here. Right? It's going to be really horrible. So for many cases, most cases. And then a final one of these 4 generic examples. Yep, let's see. The state estimator, maybe my information space. This is in fact the most common thing done in control theory and robotics. You take all your sensor information, you try to fully reconstruct the state. I consider this, well, boring, I guess. You know, most people do it, and it's great, but not very exciting for this direction I'm talking about. But it fits in the framework. We start with some initial state guess, and then we make a filter that, based on the current observation, it keeps trying to produce a state xk, which is the current estimate. And then in control theory, you may see people making controlling control theory. Feedback control looks like this all the time. That's how they write it in control books, right? Maybe they use gamma here or something. A policy. Yeah, pi for policy, maybe. It's states to actions. And then they don't know the state, so they make a filter to estimate the state, and that's what you make it. So that's another possibility. So those 4 cases are kind of nice. Let me say the 4 cases again. You can ignore all of the history and just make your decisions based on the current sensor reading. You can only keep track of what stage we're at, which is throwing away lots of stuff. You can throw away nothing, right? This is like the hermit or the collector who can't throw anything away, right? You keep all of the information. Or you take your information and you work really hard to get the state. Reconstruct the state and then move on. So those are 4 very generic possibilities. Oh yeah, here's an example of the simple state estimator. I'm just making a silly example here. So I get a history-based sensor that just looks at how much, it measures how the state changed each time, and then based on the initial state, it can just keep updating and updating. It's like what happens, what's called in math, with what's called a telescoping sum. You just can collapse everything, and you get to know at the end exactly where you're at. But it doesn't usually work like that, because as this thing says, you need a model of how X changes, and what the control theorists use for that is a control system model. So that will start to become important now. So as I said, I think I've been saying these kind of things, but the idea is that once you define this filter, you try to live in the information space. You always stay there, right? You get in new information from observations, but you continue to live in this information space. In other words, that's the space you're transitioning in. It's like your new state space, but it's the internal one that you're using for computation. So everything you need to get is done by just iterating this mapping phi, over and over again. Okay, so that's something to think about. Also note that I could make some other kind of induced mapping, kappa, if I want, which says given the initial information state and the entire history, it can compute what this thing should give. So it's just undoing the iteration. I can write it in the iterative way, which is the way I did with phi, or I can just apply the whole iteration at once to get kappa. Just kind of an interesting thing to note. All right. Well, as I said, we have to start thinking about state transitions. In other words, what happens when I do not, what happens when I do not have observations over some interval of time? Well, let's see. We want to make a filter that goes like this, and how do we know that we can get to that next information state using the previous one in YK? Right? Well, we can look at these pre-images here. These are helpful. I can take the new observation and look at the pre-image. That tells us a lot. However, I must have information about where I was before, right, based on the previous observations, but also what else do I have? So what we do is we define motion models. This would, for example, tell how the evaders move, right? There you say they move arbitrarily fast in the basic visibility-based pursuit evasion problem. So we define motion models to define how the state changes between the stages. Maybe the stages occur at some fixed delta t. Every second we get a stage. Maybe it happens at one stage may take a second, and the next stage may take 5 hours. Who knows? Depends on the problem. But we do assume that observations come later and later, right? There's an ordering to them, and that's all that's applied. And no two come simultaneously. All right. So that's very nice. And then we try to make such a mapping, and we hope that you can compute it nicely. I don't think I mean efficiently computable in the theoretical computer science sense, but I mean like you can nicely compute it. I don't know. Be careful. All right. So how does the state change when it's not being observed? Let's start with the simplest case. Let's just think about state and how it might change. So it could be the case that I don't have any sensing stuff here or anything. I'm just thinking about states and how they change. In other words, maybe that's an evader modeled by its position is modeled by xk, and it might start to change. I think I'll say a little bit about this, and then I'll kind of finish for today. But this is getting probably too much more stuff for at the very end here. So how does the state change when not being observed? So I have, in this case, this is the simplest. Maybe I can predict exactly what happens. So if I know the previous state, I know exactly where it's going to go. One special case where I can always do this is the static case, where the state never changes. Right? So maybe it's a little boring, but maybe that. Here's another case. Actually, for this case, then, if I have this model, and if I know that we're in some, let's say, x of k is the set of possible states at stage k. So if that's the case here, then I can use this model to represent this, which is the set of possible states at k plus 1 given the set of possible states at k. If that's the case, I just do this. I just say, well, it's all xk plus 1s such that there exists an xk in big xk, and you can get this equation to hold, right? So that's all. So you can actually get the transition. In other words, it's every xk plus 1 you can get by transitioning from one of your xk's. So in other words, maybe this is my xk, XK, that's the set of possible states. And then in the next time step, I have a model, so if any one of the states, I can predict exactly where I go next. It might tell me if this is my XK, then this will be your XK plus 1, right? And so I use this mapping over and over again. This F told me this, and I apply it to all possible elements in here, and then that will give me something, which is XK plus 1. Does that make sense? So that's what this is saying. Very nice name for this is called a forward projection. People have used these a lot in robotics literature. So forward projections. That's great, but what happens in practice is that the states are usually not predictable in such a nice way like this, and we have to do something about that. So there's a non-deterministic case, there's probabilistic case, and then eventually we're going to add action into it and make it look like control systems. But I think I'll stop now. I can take questions, and then I'll stop. All right, thanks. Be happy to talk to people during the break.